Welcome. We will continue our discussion on equivalence class testing. Last time we had just discussed a little bit about equivalence class testing and we will continue from there. The main idea behind equivalence class testing is that we partition the data value, the data that is input to a function, we model it and partition it into equivalence classes. Now, let me just tell little bit about why we want to partition it into equivalence classes and how does it help in designing test cases. We partition it into equivalence classes because each data point in a equivalence class exhibits similar behavior. If we think of this as a representation of a program, the control flow in a program, you can see that there are many ways the control can flow and each way the control flows represents a behavior. So, if we partition the data that is input to a program, if this is the set of data, if this is the set of data that is to be input to the program and we know that these are the data for which it follows this path and these are the data for which it follows this path. So, these represent different behavior, different output, different type of processing and so on, and maybe this one corresponds to a behavior exhibited by this and so on. Now, all the data points here, they correspond to the behavior expressed by this processing. So, the idea here between equivalence class partitioning is that if we can identify the equivalence classes for which the behavior for any class is similar for all the data points, then we can just test it with one of the data point here. So, that we know that okay, this behavior is okay, we will also select a data point that will drive it through a different behavior and so on. That is the main idea here, that a program behaves in similar ways to every input value belonging to an equivalence class. So, if this is the equivalence class, then every input will exhibit similar behavior because the set of statements that are getting executed are similar and therefore, if it works for one point here where it followed this set of statement execution, then it is reasonable to expect that it will also work satisfactorily for all other points in that same equivalence class. But we also need to check about the behavior when it follows this path and so on, this set of statements. But one thing that we must remember is that from a black box description of a functionality, that is a use case, we know that there are alternate scenarios. In the alternate scenarios, this is the main line scenario and then there are many alternate scenarios. We can think of that in the main line scenario, certain set of statements here, this is the main line scenario, and corresponding to the main line scenario, certain set of statements get executed. And for alternate scenarios, different set of statements get executed. And therefore, if we look at the use case description and look at the main line scenario and the alternate scenarios, we can associate equivalence classes to each of these. The mainline scenario, the data that makes the system execute the mainline scenario corresponds to one equivalence class, and for every alternate path we have a different equivalence class. This is one way to identify the equivalence classes, but we will see that even when it follows the mainline scenario, there may be further equivalence classes in that. We will just explore that. So, let me just repeat here that the total data input data domain, the input data domain, we model it and then we split it into equivalence classes such that the tester, or we, if we are doing the testing, the tester feels that for every data point here the system exhibits similar behavior, and then since all of these make the system execute certain set of statements, it is reasonable to execute using any one of these points. We can select any one of these points, and similarly with other equivalence classes, and that will form our equivalence test cases, equivalence class test cases. One way of identifying the equivalence classes is by examining the use case description. The mainline scenario and the alternate scenarios correspond to different equivalence classes, but beyond that we said that every equivalence class there may also consist of other equivalence classes. How do we identify that? One is based on the use case diagram and the use case description. We identify the scenarios, we examine the input data which make it execute a specific scenario, and those set of input data constitute the equivalence class. But then there are other guidelines for identifying equivalence classes, because this allows us to identify a broad set of equivalence classes, but let us see what are the other guidelines. The other guidelines are that we look at the input values. If the input is a range of values, as we find the description of the functional requirements or the use case, if the input corresponds to a range of values, let us say 1 to 100. If these are the set of valid values, then we have 3 equivalence classes. One is the valid set of equivalence classes, and there are 2 invalid equivalence classes on the both ends of the valid equivalence class. So, this is a invalid equivalence class, this is a invalid equivalence class, and this is a valid equivalence class. Now, what if the input is a set of values? Let us say only A, B, C, let us say our system, our software takes only a character, and based on the character it does certain functions. These are the menu choices, let us say A, B, C, and these are only the valid menu choices. You have to input any one of these. In that case, this defines a valid set of equivalence class, and anything other than A, B, C, these are the invalid set of equivalence class. So, if the input is a set, we need to identify a valid set of equivalence class and a invalid set of equivalence class. What if the input is a Boolean value? Again, here we have one valid, that is the Boolean value, and any other value such as a character, control characters and so on, these will constitute the invalid class. Now, let us check our understanding for two example problems. Let us say a function takes an area code, that is the pin code, and the pin code is, let us say, has value between 10,000 and 90,000. So, what are the equivalence classes here? We can see here that this defines a range 10,000 to 90,000, and therefore, there will be three equivalence classes. One is the valid equivalence class between 10,000 and 90,000, and another less than 10,000, another more than 90,000. So, the crucial thing to recognize that for the area code or the pin code, it denotes a range of values, and as soon as we know that it is a range of values, we can identify three equivalence classes, which is a valid and two invalid set of equivalence classes. Now, let us look at another one. A function, let us say, takes a password. Let us say the function is login and it takes a password, and the password consists of a string of 6 characters. Now, what will be the equivalence classes here? It is crucial to recognize that a string of 6 characters is actually a set. It is a finite set of all possible string of 6 characters, and therefore, as soon as we recognize that it is a set, we will identify two equivalence classes in this case. That is, one is a valid equivalence class, which is a member of the set, and another is invalid equivalence class, which is less than 6 characters, more than 6 characters, etcetera, etcetera. So, those are the invalid. So, there are two equivalence classes here. One is the valid equivalence class, which is a member of the set, and invalid equivalence class, all the data points which are not the member of the set. Now, let us try to solve some problems. Let us say we have a function which takes 3 integers and then determines what is the type of the triangle that it forms. Maybe the name of the function is determine triangle type, and it takes 3 integers, side 1, side 2 and side 3. Now, based on whether the triangle defined by these 3 sides, they form a isosceles, scalene, equilateral, etcetera. It defines the type of the triangle. Otherwise, if it is not a valid triangle, it will display valid invalid triangle. How do we identify the equivalence classes here? By observing the output here, the display, whether it is isosceles, scalene or equilateral, we know that these correspond to different scenarios. If we give set of values, set of 3 values which form a isosceles, then this corresponds to a scenario scalene, equilateral, etcetera. And therefore, by observing the output, we can get an idea of the scenarios and the equivalence classes that these will define. So, for this problem, the initial set of equivalence classes are the scenarios which correspond to the output in this case. But let us see if we have any general problem, a function let us say f, we have a function f which takes a parameter, maybe integer, float or something character. Let me just write integer I, f is a function which takes an integer or a float or something, then we can say that to start with we will have two equivalence classes. The set of data can be partitioned into two equivalence classes. So, these are all the set of data, and we can partition the data into two equivalence classes. One is the valid set of equivalence classes, valid set of data which is the valid equivalence class, and the invalid set of data which is the invalid equivalence class. So, there are two equivalence class for every problem we should be able to identify to start with, and then as we proceed to find further equivalence classes, we will find further valid set of equivalence classes, further valid set of equivalence classes, and further invalid set of equivalence classes. Let us see how we go about doing that. So, this says that to start with, the input data will partition it into valid and invalid set of equivalence classes, and in the next step we will further identify equivalence classes within the valid set and also equivalence classes within the invalid set. And once we have done that, of course, within the equivalence classes we might for some problems find further equivalence classes here, but once we have ultimately found the equivalence classes, then we just pick one data value from each equivalence class, and that forms our equivalence class test cases. Now, let us look at some problems and see how to identify the equivalence class test cases. Let us say our function takes a integer between 1 to 5000. These are the valid set of data, any integer value that is between 1 to 5000 is a valid input. So, this corresponds to a range of input, and we can clearly identify that there is a valid class and there are two invalid classes less than 1 and more than 50,000. Similarly, if we have a set of values like A, B, C, we find one equivalence class which is valid and another which is invalid, and then we will pick up one value here like B or C or something, and something which is not part of here maybe F or something. Now, let us look at another example. Here the program reads an input value in the range of 1 to 5000 and computes the square root of the input number. The input is a range here, can easily identify, and therefore, to start with there are three classes, one valid class and two invalid classes, one invalid class less than 1, another invalid class more than 5000. So, the set of negative integers, the set of integers between 1 and 5000 and integers larger than 5000, these are the three equivalence classes. Then we can pick representative values from each. We may choose -5, 500, 6000, or you may choose any other value, but then once we form the test cases, we assume that if it passes a valid value like 500, then any other value it will also pass. That is the assumption behind equivalence class testing. So, we can say that a set of input values constitute an equivalence class if the tester believes that these are processed identically by the program. Let me repeat that. A set of input values constitute an equivalence class if the tester believes that these are processed identically. Let us do some more problems to get a clear idea about how to proceed to identify the equivalence classes. Let us assume that we have a function issue book for a library software, and then it takes the book ID and then issues that book. But then we can imagine that the code that is there in the issue book, depending on the type of the book, it will execute different set of statements. For example, if the book ID is a reserved book, then it will execute some set of statements and it may output that the book is reserved, cannot be issued out. Similarly, the book is a reference book, then it will also execute slightly different set of instructions, and then it will say that it is a reserved book, cannot be issued. If it is a book that can be issued, it will issue it. If it is a, let us say, a multi volume book, a set of books, then it will say that this many number of books are issued out. So, based on the input, we can identify the equivalence classes. The first level, we can have the issue book. Okay, first is of course, the valid and invalid data, something which is not a book ID, maybe a floating point number or something. So, valid and invalid, and then for the valid book, we can have a issuable book and a reference book, and for the issuable book, we can have single volume and multiple volume. Let us do some more examples. Let us say we have a function which is fetch image. It takes a URL and then fetches the image and returns the image. So, the function, it takes one parameter which is the URL, and depending on the image present there, it retrieves the image and returns the image. Now, how do we define the equivalence class here? One is that based on the type of URL, for example, it may be using HTTP protocol, HTTPS protocol, FTP file. So, this is the protocol used in the URL. Based on that, we can partition into a set of equivalence classes. So, that I have written here. This is the set of data, valid data, and then based on the URL specified, we can have some equivalence classes like HTTP, FTP, file, HTTPS, etc. But again, the specific URL may point to different types of images. So, depending on the image type, we again can define a equivalence class depending on whether it is a HTML image, GIF image, JPEG, plain text, etc. So, we have another set of equivalence class here. Just want to make this point that based on the input, it is not that there is a single hierarchy, we can have multiple hierarchy based on different characteristics of the input, the URL, the protocol of the URL, the file type and so on. So, even though the concept is straightforward, but sometimes identifying the equivalence classes can be requiring some thought on the input data value. Once we identify the equivalence classes, then we just select one data point corresponding to the valid equivalence classes. So, that is single volume, multiple volume and reference, and similarly we select one data point for the invalid equivalence classes. So far we just looked at how to identify the equivalence classes when a function takes one parameter. But we can have a function which takes multiple parameters. Now, how do we identify the equivalence classes here? Of course, it is rather straightforward of the discussion that we had so far. We will examine each input parameter, and based on the input parameter we can identify the equivalence classes for the different input parameters. But now, how do we define the test cases? We can select points from here for corresponding to this parameter, points corresponding to this parameter and so on. But the test for the test case, one way is that we take one point from here and form the test case. Another way can be that we take one point here and corresponding to that we define test cases by considering each of the point here and each of the point here. So, that will give us a large number of test cases. So, let me just repeat that once we identify the equivalence classes for each of the three parameters, one way is that we define the test cases such that every equivalence class is represented in our test case. The other way is that we form a exhaustive combination of the input values. Now, we are almost at the end of this lecture. We will continue from this point in the next lecture. Thank you.